Coin piles problem from the CSES problem set. So the instruction goes as follows. You have two coin piles containing A and B coins. On each move, you can either remove one coin from the left pile and two coins from the right pile, or two coins from the left pile and one coin from the right pile. Your task is to efficiently find out if you can empty both the piles. And the input is, the first input line has an integer t, the number of test cases. After these, there are t lines, each of which has two integers, a and b, the numbers of coins in the piles. And the output is, for each test, print yes if you can empty the piles, and no otherwise. And the constraints is that we have 10 to the power of 5, so 100,000 test cases at the most. And A and B will be less or equal to 1 billion. Okay, and here we have the sample input and output. So for the first case, we're going to execute the second move, where we move two from the left pile and one from the right pile, and this will empty both of them at the same time. So the output is yes here. For this case, we cannot execute, even when we execute any of the moves one time, we will end up having one coin in one of the piles and 0 coins to the other pile. Okay, so the answer is no here. And in this case, where we have 3 to the left pile and 3 to the right pile, we can execute the moves, the two types of moves alternately. So let's execute the first move first. This will remove one from the left pile, so we're going to have 2 coins left, and 2 from the right pile, so here we're going to have 1 coin left. And then we're going to execute the second type of move, where we remove the 2 remaining from the left pile and 1 remaining from the right pile. So we're going to output yes, because they're going to empty, the piles will empty at the same time. Okay, so how we can solve this is, of course, we can brute force this A and B, but this will not suffice for the time limit of 1 second here, because A and B will reach 10 to the power of 9, so 1 billion. So we cannot brute force trying the moves here, okay? It will be more beneficial if we found a constant time solution, okay? And just see if there is a solution. Instead of finding the actual solution, we need to find a way to check if the solution exists, okay? So what I have done here is I just used simple algebra, and I found the relationship or equation, if you will, that we need to that there needs to be true in order for an answer to exist. So what I'm doing here, I declare two integers, a and b, so the left coin pile and the right coin pile. I input them, okay, and then I check if a is smaller than b. I swap a and b, so I want the left pile to always have the greatest amount of coins, because that will not change the problem essentially. The two moves that we have, which are possible here, are mirroring each other, okay? So it doesn't matter which pile is considered to be the left and which pile is considered to be right, okay? So I always have the greatest pile to the left, okay? Let's consider that A is the left pile and B is the right pile, okay? And then I'm using algebra here. So here I use X to be the types, the second type move, and Y to be the first type move, okay? So A, so the left pile, minus 2 coins every time we execute the second move, and minus 1 coin every time we execute the first move, okay? And for B, this will be actually equal to the value of the second pile when we remove 2 coins, which happens in the first move, and 1 coin, which happens in the second move, okay? And both piles will need to reach 0. So this is the equation that needs to be true for our problem for us to be able to actually to reach both piles being empty, okay? And output yes. So based on this, by the way, X and Y here should be integers, okay? Because we execute integer moves, integer times every move, okay? We cannot execute the first type of move half time, okay? It's not possible. And then based on these equations here, we extract these two equations here. So a will be equal to 2 times x plus y, okay? That's why it will become equal to 0 essentially. So if we move this to the right hand side, so to the zero part side, we get this equation here. Same goes for b. If we move this part to the right hand side, we will get that b equals to 2 times y plus x, okay? Now, because a is always going to be greater than b because of this swapping that I did here, so a will be always greater or equal to b, and thus x will be greater or equal to y. I forgot the equal sign here, okay? So x will be greater or equal to y, and that is because we're gonna remove 2 coins more times from the left pile, okay? We need to remove more coins from the left pile, so we're going to execute the second type of move in order to remove more coins every time from the left pile, okay? Since the left pile has the greatest amount of coins. Now, based on this relationship here, I rewrite x. So I replace x with y plus z here, okay? So since x will be greater or equal to y, essentially x equals to y plus another integer value, which can be 0 as well if x is equal to y. So y plus z essentially, okay? And I replace this in my equations, in these two equations essentially. I replace x with this y plus z, and I get this result. So for a is equal to 2 times x plus y, so 2 times y plus z plus y, and this gives us 3y plus 2z. And for b, it equals to 2y plus z, okay? Since we replace the x that we have here with y plus z, and the result is that we have 3y's plus 1z, okay? So if we subtract the top part from the bottom part, so if we subtract this equation from this equation, we see that a minus b will be equal to essentially just 1z, okay? So a has this extra z in its value essentially, okay? So z equals to a minus b essentially. Now we use this relationship here, and we replace z on this equation here, the 3y's plus 2z's, okay? So a equals to 3y's plus z, but instead of plus 2z's, but instead of using 2z's, I use 2 times a minus b, so plus 2a's minus 2b's, okay? And now based on this, we can, if we solve for y, we're gonna see that y equals to 2b minus a divided by 3, okay? So we know that y needs to be integer, okay? So if y is integer, x will be integer as well, okay? That's the only thing we need for our solution to exist, that the number of moves, the number of times I'm gonna execute each type of move is an integer number, okay? That's the sole requirement here. So how do we test if 2b minus a will be divisible by 3? We just use the modulo operator essentially, okay? So here we set we get this result into a value, into a variable here, which I call res. So 2 times b minus a, and now we need to check if this res, first of all, it needs to be greater or equal to 0, okay? Because we cannot have a negative y here, so the number of first type moves cannot be negative, okay? And that will also have, with that we also have make sure that y will not be negative because y is greater than x is not negative because x is greater than y. So we just execute the simple if statement as I was explaining. So the result should be greater or equal to 0, and the result modulo 3, okay? So for this to be an integer division, we have to be to give 0 in this modulo operation here. So if the result is divided by 3, the result modulo 3 will give us a 0 modulo here, okay? And if this is true, we just output yes. and we return. Otherwise, if this is not true, we just output no. And this is pretty much the solution for a problem. We just need to check this property here, that this property is true, and make sure that the number of times I execute these two types of moves which the instruction gives me here is an integer amount of times, okay? And that's pretty much it for the problem. So if you did get stuck on the problem and this tutorial helped you, please leave a like to the video, subscribe to the channel, and I will see you in the next one.